One of the most popular dimensionality reduction techniques available to us is a principal component analysis. Anytime you are working in a modeling capacity and you are given a feature set of predictors, you're going to want to eliminate as much colinearity among that feature set as possible. This will help downstream as you are concerned with ideas like stability and robustness in your model's performance when you actually apply it in the real world. So why do we care about redundancy in the first place? There's a lot of different examples and analogies we can use, but I came up with one that is my favorite, and I will give it to you through a narrative. Suppose you are a security guard, and you're tasked with ensuring that nobody is on premises past a certain time. Let's say you have 10 cameras. Let's say each of those cameras is pointed in a unique direction. Well, that's going to be certainly helpful, is it not? You're going to be able to look at your security guard screen and you're going to see each one of those camera frames individually, and you'll just scan each one of those camera frames and you will be able to determine whether or not there is somebody on the premises or not. So you need all 10 of those cameras. You need all 10 of those cameras. Now suppose that 3 or 4 of those cameras are now overlapping regions, and there's only a sliver of one of the cameras that you need to care about. Well, wouldn't it be nice to be able to combine some of those cameras with overlap into just one frame so you could quickly skim all of the frames on your little monitor to see if there's anybody there that's not supposed to be, instead of concerning yourself with rescanning all of that redundant information? That is the idea behind a principal component analysis. Essentially, what we are doing with our feature set is we are taking the overlap in the security cameras and we are cutting out that overlap and saying, hey, let's take all of this overlap, let's toss it out, and let's only look at the unique information that is explained or visualized by each individual camera up until a certain point, and then we can go ahead and cut off the rest of the redundant information, or maybe information that explains a very, very small amount of what we are interested in. So in the context of that security guard example, perhaps there's one camera that's entirely cut off by a refrigerator. That is not helping our analysis. We can toss that out, and that is going to be a smaller fraction of the variance that we are interested in capturing. So that is the analogy that I like to make in terms of redundant information, is trying to keep it visual, trying to understand that, hey, like when we are dealing with redundancy, we want to eliminate it for a productive reason. This is going to help our model's capacity to predict, to classify, whatever it is we are doing. And it's not just some hand wavy, oh, we do this upstream, as like a necessary step in the model development pipeline. No, this is a very useful, and there is an intuitive explanation as to why we go about doing some sort of dimensionality reduction, especially when colinearity is present. So in this video, we're going to talk about PCA, principal component analysis, and we are going to use a set of stocks and stock returns 2021 to 2022 as an example. So the first step is going to be to import the necessary libraries. Naturally, we're going to use pandas, numpy, matplotlib. I'm going to also import the standard scaler and PCA from sklearn. We probably won't be needing scipy, but I have it there just in case. The first thing we're going to do is load in the data. So what I've done since Yahoo Finance has gotten rid of their API is I've gone on Yahoo Finance and I've pulled data from 2021 to 2022 from a set of 4 stocks and an ETF. And what I've actually done is copy and pasted those tables into an Excel sheet and imported the data as such. So I'm just going to read each sheet name, and I'm going to combine based on the date, and I'm going to compute the log return of the close. So I have here Apple, Amazon, General Motors, Microsoft, and the S&P 500 index. I thought I had pulled it for the ETF, the SPY, but it turns out I actually used the index. So this is going to be my data frame, my data set of stock return information. Now, if we go on down here and take a look at the correlation, you can see that we have the return for Apple, Amazon, General Motors, Microsoft, and the S&P 500. And of course, the diagonals are going to be 1 because everything is perfectly correlated with itself. And then if you take a look at the correlation between the assets with each other, we get a variety of different correlations. All of them seem to be greater than 0, which does make sense to some capacity, But here we're taking a look and we see that, Apple is highly correlated with Amazon, not as correlated with General Motors, and this would make sense, right? Because they're in different sectors, but they are still exposed to some underlying market risk. Apple is highly correlated with Microsoft, which is also what we would expect, and it seems also to be highly correlated with the S&P 500. So this is quite interesting, but what we can tell here is what is this correlation an actual measure of? So this is a normalized covariance matrix, right? It's just normalized by the variance of I should say the root product of the variances. But nevertheless, this is showing that the relationship between Apple and Amazon is not orthogonal, right? There is some overlap in information, and that is this colinearity that I was referring to at the start of this video, right? So what this means is there is some redundancy in the information that is being portrayed by Apple and Amazon. There's some redundancy in the information that's being portrayed by Microsoft and General Motors, and so on and so forth. You can look at the pairwise correlations here and see, the varying levels of redundancy. But this is something that we're going to want to eliminate altogether, because we don't want to be overfitting noise in our model. We want to be capturing as much authentic explained variation as possible. So what are we going to do? Well, we're going to do a principal component analysis. First, why are these high correlations problematic? So clearly we have colinearity in our data, but what is the problem? Well, in a regression setting, when features are highly correlated, it can be difficult to determine individual effects. So in other words, when Amazon increases and has a high correlation with Apple, those are contemporaneous. Which one caused which one, and which one caused the response variable to change in this way? We don't actually know. They don't each contribute orthogonal unique information. There's redundancy. So it becomes difficult in terms of explanation. Moreover, the coefficients themselves can be unstable, right? Because should the weight be on Amazon or should the weight be on Apple? Which one is contributing to the change in the response? We don't necessarily know, and this is why it can be difficult for interpretation and modeling in a regression capacity. Moreover, we may have unstable weights in that same idea as a instability in the coefficients in a linear regression setting. We may have unstable weights in a neural network. And moreover, the model is going to be more complex than it needs, right? If we have Apple and Amazon as two separate features, when in reality we could take the unique information from each and, separate them, then we can remove the redundancy. We can remove the redundancy, making the model less complicated. Computational costs will also be, decreased. And again, you can overfit on this idea of noise, and interpretation might suffer. So there's a lot of negatives with colinearity, and a lot of times when you start your undergraduate studies, you start taking statistics classes, maybe you take an intro to portfolio management class, and you start to see it's like, okay, wow, there's like these different measures of colinearity of like VIF, and how does this actually impact my regression model? The problem, I think, is when you first start to learn this stuff, you're so focused on like what in the heck a linear regression is, mechanically how it works, what in the world does it mean to have least squares, things of that nature, that you're not necessarily seeing the downstream effects of colinearity and why we would bother to deal with it upstream. So hopefully it's a little more clear now that your model can suffer in terms of robustness, stability, and interpretability if you have redundant features, or redundancy among your feature set, I should say, and colinearity. In order to combat this, we will conduct a principal component analysis. Who would have thought this was going to be a video on matrix algebra? Not me. But let's take a look. There are two different ways we can conduct a PCA. So we know that a correlation matrix is just a normalized covariance matrix. So essentially what we want to do is we want to transform this entire matrix into a diagonal of ones, where each feature is explaining unique information and all of the off-diagonal elements are 0. This would mean that each feature is explaining unique information. And that's exactly what we would like. So what can we do in this capacity? Well, we can do two things. We can conduct this diagonalization through a singular value decomposition of the data matrix, or we can do an eigen decomposition of the covariance matrix. So supposing we had a data matrix X n by p, where n is the number of trading days and p is our number of stocks, we can find a unique decomposition. X is equal to u sigma v transpose, where u is an orthogonal matrix of left singular vectors, v transpose is an orthogonal matrix of right singular vectors, and sigma is an n by p diagonal matrix with singular values. Okay, the principal components are then going to be given by xv, which is equal to u sigma. How does this diagonalization actually work? Well, if we started with the covariance of the principal components and we expanded it using the definition, that is, this is the definition of a covariance matrix. We have, say, x transpose x. Here we're interested in the covariance of xv, so we have xv transpose xv, normalized by n minus 1. We substitute in x equal to this decomposition, the singular value decomposition, and then since v is orthogonal, v transpose v is the identity, and since u is orthogonal, u transpose u is the identity, and we are simply just left with 1 over n sigma transpose sigma, and this is in fact diagonal since sigma is a diagonal matrix. Okay, very good. So as I had mentioned, we are interested in diagonalizing this correlation covariance matrix. That is how we do it with a singular value decomposition. What about an eigen decomposition of the covariance matrix? The covariance matrix, start with the covariance matrix S is equal to 1 over n minus 1 x transpose x. This is exactly the same argument made here for xv. See, we have xv transpose xv normalized by n minus 1. Here we're using the original data matrix to come up with the covariance matrix, and that is what we conduct an eigen decomposition on. So to find the eigen decomposition, we find some v lambda v transpose, where S is a p by p covariance matrix. We are given v, which contains the eigenvectors, and lambda, which is a diagonal matrix of eigenvalues. So what we go ahead and do is we transform the data. We have covariance xv is equal to v transpose sv, which is equal to v transpose v, lambda v transpose v, and of course we are left with lambda. So first multiplying v transpose v, we get the identity on the left, and then this will simplify to the identity on the right as well, which is just I lambda I, and this is lambda, and lambda is a diagonal matrix by the eigen decomposition. Thus, we have transformed the covariance, and it is in fact diagonal. So now, let's connect the two approaches. So the singular value decomposition is connected to the eigen decomposition through the eigenvalues and the singular values squared. So what I mean to say is if we begin with a singular value decomposition, xu sigma v transpose, we calculate the covariance matrix S is equal to the normalized x transpose x, which is equivalent to 1 over n minus 1, that normalization, times v sigma transpose u transpose times the singular value decomposition here. So again, all we're doing is we're taking this SVD, subbing it into the covariance, and we are just transposing every item in u sigma v transpose, flips the direction, and it transposes all the matrices, and then we have this product, but we also know that u transpose u is the identity, and then we're left with this v sigma v transpose, and this is going to be diagonal with entries sigma I squared, and that means that sigma transpose sigma normalized by n minus 1 is lambda, and that would also imply that lambda I is equal to sigma I squared divided by n minus 1, and that is the connection between the eigen decomposition of the covariance matrix versus the singular value decomposition of the data matrix. So the eigenvalues are just scaled versions of the squared singular values. That is all we are saying. Moreover, the eigenvectors in V are the same as the right singular vectors, and both methods will produce the exact same diagonalization. So whether you choose to do the SVD approach or the eigen decomposition approach, you will end up with a diagonalized covariance correlation matrix, which is exactly our goal in the transformation of the original data matrix into the principal component space. I would certainly encourage you to walk through both arguments in Python to convince yourself that the eigenvalues are simply a scaled version of the singular values squared, but Python will make this very easy for us by using sklearn and this PCA fit transform function here. If you were to do it using the eigen decomposition way, then you would just compute a dot product of your original data matrix with the eigenvectors, and you would essentially have this set of loadings, and you can go about analysis on the loadings, which is what we're going to do in a moment. But what I want to do first is I want to show you what the new data looks like in terms of variation explained among the principal components. So what I've done here is I've dropped the market return, and I'm only looking at the return for Apple, Amazon, General Motors, and Microsoft. And what I've done here is I've conducted a principal component analysis, and I'm looking at the cumulative sum of eigenvalues. Now, the cumulative sum of the eigenvalues is going to be the normalization factor in determining the amount of explained variance by each principal component. And if you do a cumulative sum, you will end up with all of the variance or all of the variation explained in the original data matrix. So should you keep everything, right, then there's really no point in doing the principal component analysis. So what I mean is, if we take a look here, I've done the PCA and I have 4 components. So I have 4 principal components, I have 4 original components. If I keep all of these components, yeah, no doubt, I'm going to explain 100% of the variance. That makes sense. I have all of the original information just conveyed in a different way in this new PCA representation, or I should say this new principal component representation of my original data. Now, should I truncate at 3, then I'm going to be left with 3 principal components. I'm going to be left with 3 principal components, and those 3 principal components, they explain over 90% of the variation in that data, in that original data. Now that is quite productive. That is a lot of variation explained. Can we chalk the rest up to noise? Perhaps. But what I want to do is, in this specific context, I want to look at the loadings on these 3 principal components. So what are these loadings? Well, we just talked about mathematically how to get the principal components, or how to get to the principal component space, right? Once you get these eigenvectors, you can go about transforming your data matrix into this principal component space. But what does this PC1 actually represent? We know it represents, or it explains, I should say, around 55% of the variation in our data. Then when we add principal component 2, we're up to over 80% of variation explained. But what are these factors representing? Well, let's take a look at the interpretation of these principal components. What I've done is I've taken a look at the eigenvectors, or the loadings, and I've looked at the loadings for each principal component. So the interesting thing about these eigenvectors is, if we look at our original data matrix, forget the SPX, I've removed that, but we have Microsoft, GM, Amazon, and Apple. All of the eigenvectors for each principal component are going to have different weights on these features. So Amazon is going to get its own weight in principal component 1. Apple will get its own weight. GM will get its own weight, and Microsoft. So I can plot these weights for each principal component. That's exactly what I've done. So let's start with principal component 1. Principal component 1 explains 55% of the variance in our data. So if I scroll down here and I look at principal component 1, we can see that, Apple is going to get this weight. We can see that Amazon gets this weight, GM gets this weight, and Microsoft gets this weight. Now, what I would like to posit is the interpretation is not necessarily trivial and it's conjecture, sure, but we know a lot about stock returns. We know that there are 3 facets of risk driving stock returns. We know there's market risk, there's sector risk, and there's idiosyncratic risk. So what I would say is, given that all of these loadings on stocks that are pretty different from one another, right? I would say Amazon, Apple, and Microsoft are probably of the same sector, but GM certainly is not. How on earth do they all have very similar positive loadings? Well, maybe principal component 1 is a market risk component, and principal component 1 is capturing common variation in Apple, Amazon, GM, and Microsoft caused by market risk. Very interesting. So now, instead of all of these features in our set conveying the market risk redundantly in the Apple returns, Amazon returns, GM returns, Microsoft returns, we have one component, the first principal component, that is going to transform each of these into a market risk component. And that's the first principal component that would explain 55% of the variance in the data. So hopefully now you're starting to see how this is useful. Doesn't it make sense that the market risk would, or the market factor would account for quite a bit of the variance explained? It certainly makes sense to me. So let's take a look at principal component 2 now. Principal component 2. Principal component 2, so principal component 1 was blue. They all have similar positive loading, so I would call that a market component. What about principal component 2? Well, principal component 2 has similar loadings for Apple, Amazon, and Microsoft, and then a terribly different loading for GM. Well, gee, what is the relationship between Microsoft, Amazon, and Apple? I would say that they all belong to the same sector, the same industry, technology. So I would call principal component 2 a sector risk component, or a sector component, industry component. Doesn't that make sense? If all of these are tech stocks, they have similar loadings. And then you look at GM and you're like, well, hey, that's a completely different loading. And that would account for, if we add the sector component to the original market component, we're up to 82% explained variance. Now, well, like I'd say around 82. But what is interesting here is doesn't this kind of make sense? Wouldn't you expect that the market component explained a significant amount of common variance? And then given that not all of these stocks are of the same sector, that the sector industry risk component would explain less common variance? So the first component explains 50%. The second component is roughly, what, 30, 20, 27 some odd percent? That makes sense because all of the stocks in the original data set are not of the same sector, but they all have market risk components in common. So it does make sense logically and quantitatively through the argument of the principal component analysis. Now, last but not least, we have this PC3. PC3 takes us to, by the way, over 90% explained variance. We really, that's a lot of variance explained. If we go ahead and we take a look at this third component, we can take a look and we say, oh, well, there doesn't seem to be too much of a relationship going on here at all. Not at all. We see Microsoft down here, we see Amazon up here, then Apple down here, and GM's kind of neutral. I would say that this is an idiosyncratic component. I would say that this is a factor that is the unique, quote unquote unique, because I'm not talking about uniqueness in the context of orthogonal information, but I'm talking about the idiosyncratic component of risk to each of these firms individually. That is, principal component 3 is, I would say, the idiosyncratic risk associated with each one of these stocks, or the idiosyncratic component. So in the first 3 principal components, we have captured over 90% of the explained variance, and we are in fact looking at a reasonable qualitative interpretation of the loadings and the interpretation of these principal components. Now, it is not a trivial thing, and moreover, maybe sector risks dominates at another point in time. One of the frustrating things about principal component analysis, once you get to a higher level and you start applying it in maybe like a quantitative trading setting, is these components are not stable necessarily over time. Sometimes they are. Maybe if you found some real structure in your data, then these components, the loadings will change a bit, sure, as you roll time on forward, but there's no guarantee. There's no guarantee that the structure that you have found will persist, or that you've found real structure in any case. So that's one thing to keep in mind, is that taking this one step further, if you're starting to think in a modeling capacity or a trading capacity, there's no guarantee that these are going to be stable. There are other things you could do that might enhance stability. Maybe you throw an ICA in here too, but that's going to be a topic for a later date. So this is the interpretation of the loadings, and this is the interpretation of each principal component up to the third principal component. And again, that's going to explain most of the variance in our data, and I would say that that is sufficient. We need it not. There's no point in using all of the principal components. That defeats the purpose of going through this PCA in general. We're going to wrap up this video with a very canonical problem in quantitative trading, and that is this idea of non-stationarity, specifically non-stationarity in principal components. But anytime you're doing any sort of statistical modeling, one of the most frustrating things is you go about collecting a sample of data, you construct some sort of model, maybe you do a PCA, and then you deploy your model, and then these parameters that you've estimated change over time. When do you re-estimate them? Is this just a temporary deviation, or has it accumulated and it's completely different? These are all things that you have to think about. So in the context of non-stationarity of principal components, I want to emphasize this applies to the loadings. I'm going to look at the cumulative variance explained of the first three principal components over time, but this also applies to the loadings. There's no guarantee that these shapes, this structure, is preserved through the rolling window of PCA that we're about to do. I conducted the PCA on the entire set, but in reality, when tomorrow comes, that's a new observation in that set. So maybe I ditch the last observation and I compute it in a rolling capacity. That's going to be up to the researcher, up to the data scientist, up to the quant trader, etc. So what I have here now is the rolling explained variance ratio, a 60-day window. So I'm using 60 days of data to compute the explained variance ratio. And you'll see I have about a year of data. So this ends at roughly, I suppose this would be like 190 something because it goes to 252 and I'm using a 60-day window. So if you look, the first principal component, which we identified as a market risk component, explains over 60% of the variance. But as we continue to roll time forward and we get new 60-day windows, it dips below 50%. And then eventually it comes back above 50%. But in the meanwhile, what happened to the other components? Well, we can see sector risk stayed relatively neutral around the 0.25 to 0.3, maybe dipping slightly below 0.25. So really in this range of 0.2 to 0.3. So 20 to 30% of the explained variance there. And then you can see that in the time that the market component dropped below 50% of the explained variance, the idiosyncratic component seems to have increased in the amount of variance that it explained, almost even surpassing the sector at one point for this particular set of stocks. I must emphasize, for this particular set of stocks and for this given time period. Again, very, very important. So the explained variance is not constant. It changes. It changes over time. And you can see that with the 60-day window. It's very easy to see. But also these loadings, it's not as easy to visualize, unfortunately, but these loadings will change as well. These loadings are going to change as well. So, maybe there's some sort of fancy chart we could do where, we take a look at the loading in a 60-day window, and then we plot the average, and it shows like sort of like a variance window around the average loading. That'd be pretty cool. Actually, maybe I'll put that together at some point. Maybe I'll add it to the QFin package. That's a cool idea. But nevertheless, I really wanted to emphasize this component of, non-stationarity and components changing over time. It's a very, very important problem in the modeling space. Now, suppose that you've found structure that no one else has found, and you're trading on that information. Yeah, you would expect stability in those components over time to some degree, unless some crazy regime changed, which causes those components to fundamentally change. So it's not like you find the golden goose of components and then you're done, right? These things will continue to evolve and change over time, and that's why it's important to understand what's going on as you continue to maybe backtest or trade in a live capacity. You could start to see these different components change in certain ways that might lead to your favor, or might lead you to retire a strategy altogether. I hope you enjoyed this video discussing principal component analysis on stock returns, showing how to essentially derive the principal components through an eigendecomposition of a covariance matrix or a singular value decomposition of a data matrix. In later videos, I would like to do an independent component analysis as well. I would also like to show how you can merge those two techniques together, maybe even apply them to some alternative data in a trading capacity. If that's something that you would be interested in, please let me know. Other than that, thank you guys so much for watching, and I will see you in the next video.